Good day, everyone. Our lesson today is about cloud development and precipitation. And then we go to different frontal systems, different weather systems. And if we have time, we will discuss about the atmospheric pressures and their measurements. Okay. Now, remember that I sent you several reading materials. And these materials, most of them talk about different types of clouds or different cloud formations. Why they are formed, how they are formed, and how to distinguish one cloud formation or one cloud type from the others. Okay, now let us try to scrutinize these clouds we have in the sky. You see, clouds, okay, are spectacular features in the sky. Clouds add beauty, add color to the natural landscape of what we see above, which what we see above would affect the ground, especially if we look at the horizon, okay, where the land and the sky meet. So, there is beauty in clouds. And clouds appear in different types, different formation, and different colors. Yet clouds are not only important for aesthetic reasons. There are also non-aesthetic reasons. As they form vast quantities of heat are released into the atmosphere. Remember that heat coming from the ocean will evaporate the surrounding air, where this surrounding air carries what we call water in the gaseous form. So water, the surface waters of the oceans will be transformed from liquid to gas. And as this water in the gaseous form evaporate up, okay? As they reach a certain height, okay? As they reach a certain height, this water, okay, will encounter lower temperature. So, from the gaseous form, they will be transformed to liquid form, but very, very small, what we call crystals. The clouds are composed of ice crystals, very, very small. Why do we see the clouds as white and as sometimes orange and sometimes as blue and sometimes combination of different colors? My dear students, these clouds you see as white actually reflect all the colors of light. Reflect all the colors of light And when the reflector, the clouds, are able to reflect all the colors, what we see will be white. White is telling us that all colors of light, remember the colors of light, the vigor, the rainbow color, when all these colors are reflected simultaneously together, what we see on the surface where they are reflected is an appearance of white. And so, when the clouds, which is a water vapor form, is already in that stage of formation, these clouds release heat into the atmosphere. Clouds help regulate the Earth's energy balance by reflecting light or by reflecting solar radiation and scattering solar radiation, and also by absorbing the infrared energy given off by the surface of the Earth. Without clouds, the temperature, daytime temperature would be very, very high. More than or higher than the boiling point of water. Just like the moon. The moon does not have an atmosphere. So daytime temperature very high. More than 100 degrees Celsius. And the other side, which is nighttime, meaning not exposed to the sun, the nighttime temperature there is lower than the refrigerator temperature. It's negative degrees Celsius. Why? There are no clouds. And clouds are the ones that regulate, balance, heat energy by reflecting and scattering solar radiation. In the moon, there is no such thing as reflecting clouds or scattering clouds. Scattering of solar radiation, reflecting of solar radiation. And of course, without clouds, there would be no precipitation. So we have rains because there are clouds. But clouds are also significant because they usually indicate the physical processes taking place in the atmosphere. To a trained observer, they are like what we call streamers, signposts in the sky of what is happening, what kind of physical process is happening there. If you have a dark clouds, dark gray clouds, the physical process happening there is that there is so much rain being stored in that clouds. I'm referring to the nimbus clouds, the rain clouds, the nimbus cumulus clouds. They are dark gray clouds. And with that, it's like a signpost. Oh, it is about to rain, or rain is going on. So, looking at the sky, we see clouds. Clouds are telling us what kind of weather do we have. Okay, now, let me look at my notes. Let us go to atmospheric stability. We know that, and we should know as students of physics, that most clouds form as air rises, expands, then cools. That is what is happening. Air rises from the surface of the ocean because this air actually is the converted ocean water, liquid to gas. When there is evaporation, what is being evaporated there is the water in the gaseous form. It rises, then it expands, and then it cools. But why does the air rise? On some occasions, and does not rise on other occasion. And why does the size and shape of clouds vary so much when the air does rise? To answer these questions, we have to focus on the concept of atmospheric stability. When we speak of atmospheric stability, we are referring to a condition of equilibrium. And when we speak of equilibrium, it is a situation where the object in its position, in its state, does not change. Let me have an example. The marble is on what we call stable equilibrium. When we say stable equilibrium, we mean that it will continue to be in that position, in this position. And if we are going to move the marble, this marble will always go back to its original location and position. Move higher, move lower and lower, or higher and higher. If I'm going to release this one, what happens to the marble? It will move back and forth until finally it will return to its original position and location. And this kind of equilibrium, we call this one stable equilibrium. So, you have this one. You have here the marble. If we are going to apply a force that it will go up here, this marble will go back. Will go back until it finally back to its original location and position. And then, therefore, we say, this marble is under a stable equilibrium. Stable. If we have some kind of location like this, okay, a location like this, or let me have another drawing here, it will be like this. The marble will be here. Even if it is at rest. Oops, wait, wait. Sorry. Okay. I made some. Okay, I hope there. Now, this one is in stable equilibrium. Now, this one is in equilibrium. But the kind of equilibrium here, we call this one unstable. Unstable. This one, this equilibrium is stable equilibrium. Stable equilibrium. Because if we are going to bring this up, then this marble will return to its original location in a later time, sooner or later. But this one, if we are going to apply a force here, it will go down, and this marble will no longer return to its original position and location. While it is true that it is in equilibrium, because the condition of equilibrium happens only when it is at rest or in constant velocity. In reality, we cannot attain a motion that has what we call constant velocity, the same speed and direction. Probably we can do that inside a controlled laboratory, but outside a controlled laboratory, we cannot have or we cannot make an object to move with constant velocity. Okay. In the case, because there are only two kinds of bodies in the universe. Bodies that are in motion and bodies that are not in motion, meaning at rest. So, when a body is at rest, when the body is at rest rather, that body is in equilibrium. If we go by the physics of forces, the summation of all forces acting on that body that is at rest is equal to 0. And we call that result as the resultant force. Remember that everything in the atmosphere and on the ground are being acted on by a force. And in the case of the atmosphere, the force here comes from the pressure of the atmosphere. When the atmospheric pressure in one area is different in another area adjacent to that area, then there would be a production of a force due to difference in pressure. Okay, so stable equilibrium, the body, if you push that up or down, it will go back to its original location and position. But for unstable equilibrium, even just a little push on that body will no longer return to its original location and position. Applying these concepts to the atmosphere, we can see that the air is in stable equilibrium when, after being lifted or lowered, this air tends to return to its original position or location. In other words, this air that is in stable equilibrium will resist upward and downward motion. Okay. But air in unstable equilibrium, this time unstable, the previous one is stable. Air in the unstable equilibrium will not return to its original position and location. A little push of that air move farther away from its original position and location. In other words, when there is a vertical air current, we say air current, moving air or wind. Okay. And there is a group of air, we call that air mass. When there is a wind, by the way, wind is produced by difference of pressures. On the map, we see pressures as lines. On the surface map, we see pressures as lines. So, on the weather or on a surface weather map, okay, let us say this is let us have Negros. You see some lines like that, okay, and lines like this very far. This line represents a certain value of pressure. We call this line as isobar. So our isobars are lines on the weather map which indicate a particular value of the atmospheric pressure. The normal atmospheric pressure is equal to 1013.25 hectopascal, where 1 hectopascal equals 100 pascals. Pascal here is in honor of the person that pioneered the study of pressure. Pascal. So 100 pascals. Okay, but we just use the abbreviation of Pascal. Where 1 Pascal in terms of force, 1 Pascal is equal to 1 Newton per square meter. That is 1 Pascal. Okay. So, remember, Pascal is a unit of pressure. Pressure is equal to force acting on a given area. force per unit area. So force here expressed in newtons per square meter, or symbol of Newton and square meter. That is the unit of pressure. In weather or in meteorology, we use a technical name, a special name for Newton per square meter. Instead of using Newton per square meter, we use Pascal. Okay. So Pascal. Then, we do not use, or we can use actually, Pascal. But meteorologists, instead of using Pascal, we use hectopascal, where 1 hectopascal equals 100 pascals. Okay. You get that? Now, so, the air mass means the air mass, it is a group of air, a body of air. It could be cold air or warm air, as large as the whole Philippine Islands, the whole Philippine Archipelago, or as small as Negros Island. That is what we call air mass. So, there are air masses that are unstable. There are air masses that are stable. Now, in order to explore the behavior of rising and sinking air, we must first review some concepts. Now, you have seen a balloon filled with air, and filled with a gas, let's say helium gas. Helium gas is lighter than air. That's why when you put that into the balloon of course will be filled with helium gas, and if you release the balloon, it will move up because the gas there is lighter than air. The helium gas is lighter than air, so it goes up. As the balloon goes up, there will be a change in pressure because as you go up, pressure decreases. When pressure decreases, the surrounding air, therefore, in terms of density, becomes smaller. So, lesser pressure. The helium gas inside the balloon will expand. It will expand until finally the balloon could no longer support the expansion of the helium gas inside it. What will happen to the balloon? Boom! It will explode. Okay. So, when that balloon rises, it moves into the region where the surrounding pressure is lower. Okay. Because there is, and then therefore the air molecules of helium will expand. Because pressure decreases. If pressure decreases, the volume increases. Okay. Now, let me go to my notes here. Now, suppose we release a balloon. A balloon-borne instrument we call radiosonde. Pronunciation here, radiosonde. Sondi. What is a radiosondi? You try to Google radiosondi, ha? Okay. So what happens is that, I will go to my notes, that will help us determine the stability of air. Okay? And the stability of the air, of course, depends on the temperature of where the instrument is located. Okay. So, you have that temperature of saturated air and unsaturated